Okay, so we are very happy to have Sumeyra Sakalli today. She's from Planck Institute for Mathematics, and we will hear about exotic form manifolds today. So you can start. Okay, thank you.
Thank you very much again for your invitation and introduction. It's a great pleasure to give a talk in your seminar. My research is in symplectic and low-dimensional topology and algebraic geometry and complex surfaces. And today I will try to give a brief overview about my research. So in the introduction, I will mention basics. I will give some definitions without being technical. And then I will give a brief history of exotic form manifold constructions just to give a motivation for the subject. And then I will also mention some open problems. And then in the second part, I will talk about our constructions of exotic form manifolds via pencils of genus 2 curves. These are complex curves. And this work is joined with Akhmedov. And in the last part, I will talk about my constructions via pencils of genus 1 curves, if time permits. So let's start. First of all, when I say a small manifold, it means a manifold whose Euler characteristic is small. And exotic manifolds are smooth manifolds. They are homeomorphic, but not diffeomorphic to each other. So topologically, they are the same manifolds, but their smooth structures are different. And in my research, I'm mostly working in dimension 4. And I want to mention this dimension a little bit. Why is it interesting, or how is it different from other dimensions? Well, let's first look at open case. Open manifolds means that these are non-compact without boundary. And for those, if the dimension is different than 4, then there is no exotic Rn. So for the n-dimensional real vector space, if the dimension is not equal to 4, then it admits a unique smooth structure up to isotopy. So there is no exoticness in other dimensions. But when n is equal to 4, then there are uncountably many exotic copies of R4. And this is the result of conf. So in dimension 4, it is quite different than others. And let's look at closed case. For closed manifolds, closed means compact without boundary. Each closed n-dimensional manifold for n is different than 4 admits at most finitely many exotic copies. So they cannot have any infinitely many, but they can have only finitely many exotic copies. But only in dimension 4, there are many known form manifolds. They are simply connected, closed, and they have infinitely many exotic copies. And here, please note that it is an existential statement. We say that there are, but there are also some manifolds, and for them, we don't know whether they exist, they admit an exotic copy or not. And I will mention them also. But here we just say that there are many of them, we know them, and they admit infinitely many. And in this sense, dimension 4 is the most different, the most unexpected dimension. And I'm working in this dimension. And in my talk, all the manifolds will be smooth, closed, and oriented. Well, inside smooth manifolds, we have a more special class. It is more restrictive, but it is more richer. We call them symplectic manifolds. And here is the definition for any dimension. So a symplectic manifold is given in this way. It is a smooth manifold M together with a closed non-degenerate differential 2 form omega. And from this definition, one can prove that all symplectic manifolds are orientable and they are all even dimensional. And we have a nice diagram. It shows us the relationship between different structures in a closed case. So let's consider this outermost space as the world of closed topological form manifolds. And inside topological manifolds, we have closed and smooth form manifolds. These are again more restrictive. And inside we have almost complex ones. And inside those we have complex surfaces. So these are complex too, but real 4-dimensional manifolds. and we have symplectic four manifolds. And complex surfaces and symplectic manifolds have non-empty intersection. And inside we have more special classes like Kähler manifolds or like Stein manifolds. And there are many others. So in my research, I work mostly with complex surfaces and symplectic four manifolds. And they are restrictive, but these are richer, I would say, because in the existence of such a structure, we have more tools, more techniques to work with. So there are many tools, they work in the symplectic category, but they don't work in the smooth case. Okay. And now I want to give a brief history of closed exotic four manifold constructions. It is not very detailed, but just to give an idea, I will just list some results. So as far as I know, in dimension 7, exoticness starts in dimension 7. And Milner showed that there are 28 exotic 7-dimensional spheres. And I think this word is his terminology. I think Milner introduced that, and it is due to him. And if we again go back to dimension 4, the first smooth orientable and exotic four manifold is due to Donaldson. And he showed that Dolgachev's surface is an exotic copy of a complex projective plane blown up at 9 points. And it was in 87. And after Donaldson, so many other constructions have been made. In the literature, there are many other exotic four manifold constructions, exotic copies of CP2 blown up at 8 points, going down to 3 points. And these are constructed by many people in many different ways. There are various techniques. There is lots of literature, and I didn't attempt to list all the names, but you know, if I tried, it would be like 2 or 3 pages long. There are many different papers. But lastly, let me mention one last result. The exotic copy of complex projective plane blown up at 2 points. So these are due to Akhmedov and Park, and then also Fintushel and Stern. And today, these are the smallest known exotic four manifolds. Again, small means Euler characteristic is small. And we don't know whether we can do even smaller than those. And there might be, again, some alternative constructions of them. There are some recent papers, but I don't remember the details. But there are various constructions. Now let me mention some open problems. In the smooth category, we ask this question, do there exist exotic four-dimensional sphere S4? And as far as I know, it is still open. You can correct me if there is a recent progress. And the conjectural version of this question says that there is no exotic four sphere, and it is called the smooth Poincaré conjecture. So mainly the conjecture says that if you have a manifold which is homeomorphic to S4, then it must be diffeomorphic to it. And we don't know the answer. And today, it is one of the major open problems in geometric topology, or low-dimensional topology, let's say. And in the symplectic setting, we ask similar questions in the same way. Do there exist exotic complex projective plane, or CP2 blown up at 1 point, or S2 cross S2? And these are all open, and still we don't know the answers for those. Let me talk about this last question a little bit. The exotic S2 cross S2s. Again, the existence is open, but there is a progress in that direction.
Sumeyra, can I ask a question?
Sure.
When they constructed these exotic structures on this, I guess Akhmedov, Park, and other ones,
yeah.
Do they construct just one? Or is there an example where they found infinitely many structures?
Actually, all of them are infinitely many. In dimension 4, yeah, all of the non-exotic manifolds admit infinitely many copies.
Okay, thank you.
You're welcome. And here I will introduce a notation. So let's say that n S2 cross S2 denote the connected sum of n copies of S2 cross S2. So we take n copies of them and connect some. And n is the B2 plus of the manifold. Then last year we have showed this result. It is joint with Akhmedov and Park. We showed that there are infinitely many symplectic and also non-symplectic exotic copies of n S2 cross S2s, for n is an odd integer and n is at least 27. And here we want n to be an odd integer because it is coming from Noether's formula. To have a symplectic structure, the B2 plus must be odd. So we need this condition here to get symplectic exotic manifolds. And previously, this result was known for n is at least 175. So in our work, we have made much more smaller constructions. Okay. Now, after 1 year, there is now a recent preprint, and in which they prove the theorem for n is at least 23, and so n is odd again, and basically they make this number down by 2 factors, and they use similar ideas, similar techniques as in our paper. So how about exotic manifolds of these types? So here I take n connected sums of CP2s, connected sums of, again, m copies of CP2 bars. We connect all of them. And CP2 bar means complex projective plane with reverse orientation. So now I'm looking at this type of manifolds. And a remark, if you have such a manifold, then when you add up the coefficients, it gives you the second Betti number of your manifold, B2. And their difference gives us the signature of the manifold. And this is a topological invariant of our manifold. And we have this older result, again, joint with Akhmedov. And in this case, we work with manifolds of this type, and they have signature 0 manifolds, and n is at least 12. And we show that, again, there are infinitely many exotic copies of such manifolds. They are minimal. Minimal means that inside our manifold, there is no -1 sphere. There is no exceptional curve, so you cannot blow it down more. These are the smallest that we can get. We show that some of our manifolds admit symplectic structures and some of them do not admit symplectic structures. And again, this result was known for higher values of n, like for 25, and we have made smaller constructions. And in this work, we work with complex surfaces. They are obtained as branched covers over CP2. And for those complex surfaces, we analyze them from the topological viewpoint. We work with them, and inside we have found nicely embedded symplectic submanifolds. And to those manifolds, we also work with other symplectic form manifolds. We combine them by using certain symplectic operations. And then also there's a way to get non-symplectic ones. So there is some algebraic geometry involved in our work. And on the same paper, we also have this result. So here, the first case, M has signature equals 1. And this one is the signature of the manifold is 2. And this is signature equals 3 case. And for all of them, again, we have made infinitely many exotic copies of M. And n takes these values, 14, 13, and 15. And again, previously, these results were known for higher values, and we decreased them. But this was for the introduction, and just a brief overview. Now, I will be more detailed, and I will talk about our another work. This is joint work again, and we have made constructions via Genus 2 pencils. Let me start now. In this work, we have worked with symplectic or smooth and symplectic operation. These are called generalized rational blowdown surgeries. These are due to Fintischau-Stern and Park. And let me give the main idea of that surgery. So let's say that you have a smooth four-dimensional manifold X, and your X contains a particular configuration of transversely intersecting two spheres. So you consider a configuration, and we say that let's see PQ be the close neighborhood of this configuration, and the boundary is a length space. I will give more details for this part in a second. And then under certain conditions, you can replace that closed neighborhood of spheres, and then you can replace that with the rational homology ball. And it gives you another new manifold XPQ. So they have defined this operation in the smooth case. And this CPQ is not arbitrary, of course. And let me say how we construct that. So we take P and Q in this way. These are relatively prime integers. And then we look at this ratio. It is the Hirzebruch-Jung continued fraction expansion, P squared over PQ minus 1. And out of it, we obtain these integers. And then according to these numbers, we construct such a plumbing diagram. And here in this diagram, every dot denotes a bundle. It is a disk bundle over the two sphere. And when there is an edge between the dots, it means that these bundles are plumbed together. It is fiber to base identification. A part of the base is identified with a generic fiber of the other bundle. And these numbers are coming from our expansion. We take their negatives. And these are the Euler numbers of our disk bundles. And this is called CPQ. Or if you like, you can just consider the bases of your bundles. Or on the base, we have S2s. And this is the neighborhood of those spheres. So these are, in fact, transversely intersecting spheres. And you take the neighborhood of that. And these numbers are the self-intersections of those spheres. Anyways, when you are able to construct such a plumbing inside your manifold, then you can take it out. And the boundary of such a manifold is a length space. It is the result of Kesson and Herrer. And that length space also bounds a rational homology ball with certain properties. Therefore, you can do this replacement operation. They have the same boundary, and you can replace this one with the other one. And I will skip the rest, but let me emphasize that Symington proved that this operation can be done symplectically. So if you start with a symplectic X, and if your spheres are all symplectically embedded, then at the end you get a symplectic four manifold. Okay, and let me give our result. So let's say M is one of the following four manifolds, either CP2 blown up at 7 or 6 points. Then for each of them, we show that there exists a minimal and simply connected and symplectic four manifold, which is an exotic copy of M. And in our work, we obtain these exotic manifolds from a specific fibration. These are Genus 2 fibrations. And in this theorem, our Genus 2 fibration has two singular fibers. They are called type 8.1 and 8.4. And I will show their pictures in a minute. And we work with them. And we also work with some operations, two spherical deformations that we defined, introduced in our paper, and symplectic blow-ups, and generalized rational blow-down surgeries. And now I will give the proof idea. I will give some details for this theorem. And I need to introduce some notations. So Fn, n is a non-negative integer. It denotes Hirzebruch surfaces. So these are holomorphic S2 bundles over S2 with holomorphic sections of self-intersections plus and minus n. We have two sphere sections and self-intersections are in this way. And another notation, sigma G denotes a two-dimensional, compact-oriented and connected surface of genus G. And when we say MCG of sigma G, it is the mapping class group of that surface. And it is the group of isotopic classes of orientation preserving diffeomorphisms of sigma G. And it is generated by Bain twists around the simple closed curves on your surface. And now I need to mention a classification result. Classification of singular fibers in fibrations of genus 2 curves. And this is the work of Namikawa and Ueno. So they gave the geometric classification of all singular fibers in genus 2 fibrations. Let me be more precise here. So they work with such a family. This is a fibration. And the fibers are complex genus 2 curves. And the base is a small epsilon disk D. And the total space X is a non-singular, complex, analytic, and minimal surface. So it is a complex surface. And our map pi is smooth over the punctured disk. So because of that, for any point you take in the punctured disk, its fiber upstairs is a compact, non-singular curve. In fact, it is a Riemann surface of genus 2. And the restriction of our map pi to the punctured disk is just a topological fiber bundle. And they work with in this complex setting. And then over the origin, there is a singular fiber. And for such families of curves, they classified all types of singular fibers. So they work with polynomials, and according to the roots of those polynomials, they have a nice algorithm. And they draw all singular fibers. They have a long list. And in our work, we work with their classification. And in the theorem, we consider these two fibers. On the left, you see fiber of type 8,4. It is a configuration of spheres. Here, every line denotes a 2 sphere. And the self-intersections are all -2. Except this first one. This one has self-intersection -3. And so we have some irreducible components. These are spheres. And the multiplicities are also different for each component. They have different multiplicities. And on the right, we have this cusp. It is what they call fiber of type 8,1. It is called 2,5 cusp. And I will also talk about that in more detail a bit later in my talk. So we considered these two in our work. And so Namikawa and Ueno studied this local picture. So their fibrations are over some small disk, and there is only one singularity in their work. So how about if you want to consider fibrations over the 2-sphere S2? Then what do we know about this case? Now, I will talk about this now, and I will give some definitions again. First of all, a fibration is called relatively minimal if no fiber contains an exceptional curve. If there are no -1 spheres, then we call them relatively minimal. And it is called isotrivial if all smooth fibers are isomorphic to each other. And moreover, when you consider such a family of complex curves over CP1, and if the genus of your fibers are at least 1, then it is known that such a fibration admits at least 2 singular fibers. So 2 is the minimum possible that you can get. And there is a result by Gonclu and Ten. They show that there exists a relatively minimal and isotrivial fibration of genus 2 curves, genus 2 complex curves over CP1 with 2 singular fibers of types 8,4 and 8,1. So they also work with Namikawa-Ueno classification, and they show that these 2 fibers are coming together inside a complex surface S. And this is their total space. So they come together. It's great. But when you want to work with them, so let me go back here. So now, thanks to their results, we know that these two fibers are coming together inside a complex surface. But we need to know whether there are sections or not. And to figure out the sections, I did need to work with modal Weyl group of that algebraic variety. So here S is our variety, and we work with the modal Weyl group of that, and it is the group of sections. And I compute the rank, and then we show that there is at least one section of that fibration. And then next, we also figured out the interactions of the section with the singular fibers. And these are coming from, as I know, algebraic geometry. And let me show the picture again. So I have these two fibers, and I show that there is a section, and it hits this component of on the left for this long chain of spheres. It hits the end component, and it also hits my cusp on the other side. After I showed that there is such a section, then I work with a contractionmorphism, and we are contracting -1 curves successively. We do successive contractions, and then out of it, I showed the existence of a pencil. So I wrote it here. We showed the existence of the pencil. It lies in the second Hirzebruch surface F2. So in my picture, I'm in this first figure. It is my pencil of genus 2 curves, and it lies inside second Hirzebruch surface. Well, here F denotes the fiber class. It is a sphere fiber. And C0 denotes the class of the -2 section of my Hirzebruch surface. And next, I take their formal sum. So I'm taking 2 times C0 plus 5 times F. And that formal sum is a member of a very ample linear system. And then in that system, we are able to find some other members like B curve. It is an irreducible component of that very ample linear system. And they also intersect at this spatial point P. It has higher multiplicity. And so after I showed the existence of this pencil, then we do blow-ups. We can do blow-ups symplectically. It is the result of Akhmedov. And by doing symplectic blow-ups, I obtain this configuration on the right. And if you notice the black part here, the configuration of these black curves, it is our fiber 8,4 that I showed you above. And I'm reaching all homology classes. I reach the correct multiplicities and correct self-intersections, and everything fits very well into the list of into the singular fiber of Namikawa and Ueno. So I'm giving an alternative construction of their singular fiber in this work. And this red curve is the section, -1 section of the fibration. And I also have this blue part, and this is my B curve here. It is blown up many times, and I obtained such a class. And by adjunction formula, you can show that this blue curve has genus 2. So it is just a generic fiber of the fibration. It is a genus 2 real surface. It is also complex. Okay, and this thing is happening inside this form manifold CP2 blown up at 13 points. Well, great. I obtained this. And I also know that from the result of Gong, Lu, and Tan, this singular fiber has a complement that I again showed the picture. It is called 2,5 cusp. Now let me describe this a little bit. What is that cusp? Well, it is the zero set of this polynomial inside C2. And in fact, when you intersect this zero set with three-dimensional sphere, it gives you the 2,5 torus knot. And if you intersect the zero set with the four ball, it gives you the ciphered surface of that torus knot. And as I know, it is the result of Milnor. And more topologically, let's say, I want to understand this cusp, then we work with the monodromy. And the monodromy is this word in the mapping class group of sigma 2. And I will explain this a little bit. So let's say that I'm taking this genus 2 surface. It is my generic fiber in the fibration. And on the sigma 2, we have the standard simple closed curves, A1 up to A5. And when we say this word in the mapping class group of that surface, it means that each letter here, each AI, is a daintivist around the corresponding loop on our surface. So these are just daintivists, and it is an element of the mapping class group. And in fact, if you want to consider the Lefschetz fibration picture locally, let's say that you have a Lefschetz fibration over some small 2 disk. And again, over the origin, let's say that I have this cusp. So how do we obtain this cusp from a generic fiber away from the origin? I mean, on the base, you take a point which is away from the origin. And upstairs, there is this generic fiber, sigma 2. And in the base, as we approach the origin, upstairs, you start with a generic fiber, sigma 2. And then gradually, you are shrinking these 4 curves to a point. When you do that gradual shrinking thing, it gives you the 2,5 cusp. So A5 remains, and so you get a sphere because you don't pinch that. But because of these 4, you get a singularity. And it is what we say 2,5 cusp. Okay. Next, by working with the monodromy of that cusp, out of this word, we obtain 2 different words. It is purely algebraic. Some relations we used. And geometrically, let me tell you what we are doing here. So the sketch is like this. We start with our cusp. Our section hits that cusp as well. And then out of this cusp, we obtain 2 components. These are spheres, S2s, and each of them have 2 double intersection points on them. So this part, passing from the cusp into these spheres, is the mapping class group. So algebraically, we are doing that. And next, at these 4 points, I'm blowing up those, and we do blow-ups, and we obtain this configuration. These are all spheres. And here we should note that this is our section, E13. It hits these 2 spheres. And above, remember, it was also hitting my other singularity. So it is the same section that I'm talking about. And it also hits this long chain of spheres. And then I combine them all together. We take this long chain, and then with the existence of section, we know that we also have these additional spheres. And we do symplectic resolutions, and we used most of them. And we obtain such a plumbing diagram from those spheres. And we get such plumbing, and it's lying inside this 4 manifold. And then, as you may guess, we do rational blowdown. So from that manifold, we take out that plumbing, and we replace that by the rational homology ball. And this is our manifold. We call it Y, and it is symplectic. Then we show that it is an exotic copy of CP2 blown up at 7 points. To show exoticness, there is a certain process. We do computations. First, you determine the homeomorphism type of your manifold. We show that it is homeomorphic to this. And here we compute topological invariance, fundamental group, and then we use the Friedman's classification result. And then to show that it is not diffeomorphic to the other manifold, we use some invariants. In this work, we used the symplectic Kodaira dimension, and it is a diffeomorphism invariant, and it was shown by Tian Junli. And I put the definition also for that invariant, but I will skip that. But if you are wondering later, we can talk if you like, but it is mostly technical. And briefly, let me say our another theorem. Again, on the same paper, we showed that, again, we constructed exotic copies of this manifold. And in this theorem, we work with another genus 2 fibration. But now the singularities are of different types. They are called type 5 and 5 star. And I will only show the picture. First, I show the existence of this pencil inside the 3rd degree Hirzebra surface. And C infinity is the +3 section, I think. And we show the existence of this pencil inside this surface. And then out of it, again, we construct one type of singularity, this black part here. Again, it is on the Namikawa ONO list. And then I work with this singular fiber, and I work with its complement, and we made our constructions. That it is similar, so I will only say this much about that part. And let me pause here to see if there are any questions. You can stop me any time.
What is Mordell-Weil group for a genus 2 fibration, and how do you compute it?
Mordell-Weil group, it is for an algebraic variety. We call it, it's the group of sections. Maybe it is an,
in what sense is it the group?
in which sense? Sorry, I didn't understand.
What is the group operation? I mean, usually you speak about Mordell-Weil of an elliptic fibration, but not of genus 2. How do you multiply sections? And how do you compute this group?
Well, for the, we are interested in the rank of that group. Let me show that again. So in fact, where is that? Let me find that at first. So in fact, here we have this S, and it is an algebraic variety. And then for that, I think the Mordell-Weil group is well defined.
No, it's defined for abelian varieties.
Abelian variety. Maybe it is also abelian. I didn't pay attention.
Why? So that's exactly the question. I mean, how do you multiply sections?
We don't multiply sections. We just compute the rank. We compute the rank of that group, and the rank gives us the number of sections inside your manifold.
Rank is the number of sections.
Yeah.
Very strange. Okay, I don't.
There's a paper I can send you. In fact, they compute such things. They have a formula, in fact.
Okay, I would appreciate the paper.
Okay, sure. Okay, any other questions?
Well, I mean, for the computation of the rank, you are using some kind, well, some version of Schroeder's theorem for elliptic fibrations or what?
So we have this analytic complex fibration. And these are complex genus 2 curves. And these are over 2 sphere. And there's a work which directly fits into this picture.
Okay, please send me the paper.
Okay, I will. Okay, whether abelian or not, I should also check that. Okay, now in the last part of my talk, I have 10 minutes, I guess, right? Let me just give the main ideas then. I will not go into much details. This is another work, and in that I have made constructions via genus 1 pencils. And let me give a few more definitions here. Let's say that we have a closed, simply connected and symplectic form manifold. And for that, we have these invariants. C1 squared is defined in this way. It is 2 times Euler number plus 3 times signature of your manifold. In fact, it is the square of its first Chern class, because X has an almost complex structure, and you can talk about that. and chi-h is Euler number plus sigma over 4. These are two numerical invariants of your manifold X. And we have a geography chart. It is coming from the theory of complex surfaces. And it is the C1 squared and chi-h chart. And on that chart, we have some special lines. And the notary line is given by this equality, C1 squared equals 2 chi-h minus 6. And the half notary line is C1 squared equals chi-h minus 3. And in my work, I have made constructions lying in between these two lines. And also recall that for minimal complex surfaces of general type, the notary inequality holds. So all such complex surfaces are lying above the notary line. But when you consider such symplectic form manifolds, it's not true. You can have many manifolds lying below that notary line. And in my work, I have worked with, again, symplectic operations. These are called star surgeries. These are due to Karakurt and Starkston. And they introduced them. And again, I will give the main idea. So from your symplectic manifold, you are cutting out a star-shaped plumbing of symplectic two-dimensional spheres. And you take it out and you replace that with a complex convex symplectic filling of strictly smaller Euler characteristic. So when you do this operation, you are decreasing the Euler number of your manifold. And also later, Laura, Starkston showed that infinitely many star surgeries are not equivalent to any sequences of generalized symplectic rational blowdowns. So some of them, some star surgeries can be written as a sequence of rational blowdowns, but infinitely many of them cannot be written. So infinitely many of them are different than those previous operations. And let me state my theorem. I showed that there exist simply connected and symplectic form manifolds. They have exotic smooth structures. And some of them are lying on the notary line, and some others are lying between the notary and half notary lines. And I obtained them from star surgeries and also by using complex singularities. And in my work, I also presented a completely geometric way of constructing certain configurations of complex singularities in the rational elliptic surfaces. The rational elliptic surface means just CP2 blown up at 9 points. And inside those, I have obtained certain configurations. And I didn't use any monodromy arguments. And I was going to give more details, but there is also another work. Maybe I should say a bit more. Just then let me give the proof idea. I will skip them. Basically, I work with Kodaira's classification and I work with cubics. So let me give the sketch of one of my constructions. In my work, I have studied pencils of cubics lying inside CP2. And here is just one construction. In that one, I work with this pencil of cubics inside CP2. So here Q and P are the base points of that pencil, and their multiplicities are adding up to 9. By Bezout, it must be the case. And C1 is an irreducible cubic, C is another irreducible member of that pencil, and Q is a conic, degree 2, and L is a line, and we take their union, and it's another member of that pencil. And then out of this configuration, I obtain these 3 singular fibers. Again, every line you see here is a sphere. These are all -2 spheres. First, I obtain these 3 inside E1. E1 is CP2 blown up at 9 points. And then by doing some other operations, I'm passing to some larger, bigger manifolds, ENs. Here in this picture, I obtain that inside E5. It is a form manifold, and the -5 is its section. And I obtain this. And then next, out of this configuration, At certain points, I do blow-ups. At certain points, I do symplectic resolutions. And I obtain such a star-shaped plumbing diagram. Again, every dot is a sphere, and H means they are transversely intersecting. And then to that, I apply star surgery, and I get a manifold T. And next, I show that it has certain properties, as I wrote in my theorem. It is symplectic, it is simply connected, exotic, and it is lying on the Noether line. And in my work, I also work with other types of configurations and other types of star surgeries. And I made other exotic four-manifold constructions lying between the Noether and half Noether lines. And here the interesting question would be, can you get such kind of manifolds lying below the half Noether lines? As you try to get more and more down on the geography chart, it gets harder and harder to come up with such kind of manifolds. And there are conjectures, in fact, related to that. And I'm mostly working with that question nowadays. And I want to close by with another advertisement. It is another work. Recently, we defined some symplectic surgeries, and their origins lie in the singularity theory. It is joined with Akhmedov and Karakurt, and we call them generalized chain surgeries. And in our work, we use singularity theory and contact topology, symplectic topology, of course. There are many things, and I have 3 minutes, and I cannot define them. But briefly, let me say that we have worked with Briscorn type singularities in this work. And we define our operations by exchanging two Steinfeldings of the canonical contact structure on the links of Briscorn singularities of this type. And I'm not defining anything, unfortunately, but let me just say that. And then we give two different interpretations of our operations. One is a symplectic sum, and the other one is a monodromy substitution. And then we also work with more general type Briscorn singularities, PQR type singularities. And we describe the Stein-Handel body diagrams of Milner fibers of those Briscorn singularities. And it is just a quick giving our work. And I think I'm gonna stop here. Thanks for your patience.
Okay, thank you very much, Sumeyra, for the nice talk. So are there any questions for Sumeyra?
Can I ask a question?
Sure.
Yeah. Okay, so could you put your work in a context? As far as I understand, nowadays there are lots and lots of examples of exotic form manifolds.
Yeah.
So people are mainly trying to construct something which would be, well, minimal in some sense. Mm-hmm. So what is special about your examples? Are they minimal in some sense, or what?
Great. In fact, yeah, in my work, I was trying to get minimal examples. But in the literature, there is a conjecture. In fact, they say that below the half Noether line, whether can you get a manifold which has only one basic class, one Seiberg-Witten basic class or not. And it is not known, as I know. And I was trying to, work with that question, in fact. It was my motivation.
What about the first one? So it was, as far as I remember, CP2 plus 7 CP2 bar. I guess it's flawed, I think.
Yeah, great. Thanks for asking. So you are right. In the literature, there are various constructions of those. The difference of our work is the first one which uses genus 2 fibrations. In all previous ones, people use genus 1 elliptic fibrations. They use Kodairas classification of singularities. And in the elliptic case, everything is well understood. The computations are easy, monodromies are super easy. And there are still many different constructions just by using elliptic fibrations. And in our work, we just work with genus 2 case. And here things are getting a bit more complicated. It is the difference.
I see.
And these are minimal. If you are asking, yes, these are minimal.
Okay, so it's minimal in the sense no -1 curves.
Yes, correct.
But okay, and you prove that these are exotic, but do you know if they are homeomorphic to some other known examples?
Good question again. So in the literature, there are many other exotic copies of these manifolds. Ours are also exotic copies. But when you take two different exotic manifolds, which are constructed in different ways, we don't know whether they are diffeomorphic to each other or not. We don't have any invariant. We can only distinguish from the standard ones, but we cannot distinguish these exotic manifolds, and it is an open question.
Well, it's not quite open. I mean, so the Rachel surfaces, they're all pairwise distinct.
Yeah, I mean, when you start with a certain way and you are getting infinitely many exotic copies, and in this case, you are able to distinguish them. But let's say that someone else made another construction in completely different way. They use another type of symplectic operation. And then they come up with the same type of exotic manifolds. And then no one knows how to distinguish these two. That's what I mean.
Okay, thanks.
Welcome.
Okay, any other questions? Okay, so let's thank Sumeyra again for
Thank you very
this
much.
talk. Thank you very much.
Thanks.